Now we have a case of a moving control volume. This is a problem from your exercise. For an automobile moving along a highway, describe control volume you would use to estimate the flow rate of air across radiator. Explain how would you estimate the velocity of that air. So here nothing concrete is given and nothing absolute is required to be solved. We only have to estimate certain parameters and write some equations based on those estimations. But let's go through it because this is the case of moving control volume that is fixed, that is not deforming. Its shape is fixed, but it is moving, just like in the example of an aeroplane and its jet engine. So this is how inside of a car looks like. Almost this is our radiator. This is our radiator, and this is our object of concern. So first of all, we have to draw a control volume for this radiator, or estimate and control volume for this radiator. So just like we did in the aeroplane example, we took the control volume as the jet engine was taken as the control volume. So here now I'm going to take my radiator as my control volume and draw a block diagram of it, or a free body diagram that you would like to call it like this. So this is my radiator now, and I am going to estimate the velocities around it now and the flow rates in and out for the coolant. My first assumption will be the regarding the flow rates. That is, let's suppose this is if is the flow rate of the fluid going in and flow rate of the fluid going out. So I would like to estimate this, that these two quantities will be equal, because we want to control the flow rate and we don't want any leakage of fluid from the system. So we would like to say that the mass is not actually changing. In this case, it is very much conserved. So the flow going in and the flow going out might be the same also. So this is what I'm estimating. You can not agree with me. You are free to do that. So if you think otherwise, you will be correct to do so, because the temperature of the fluid is changing. So this might change the density of the fluid. So you can say that the flow rate in this case shall not or could not be equal. But what I am estimating is that the flow rate is going in of the coolant and going out is equal, and I will concern more myself with the velocities of the air and this control volume that is going through this radiator. So first of all, my velocity of vehicle, that is velocity of my car. So the car is moving, let's suppose, in this direction. So this will be the velocity of my car. My control volume is fixed inside this car, and this is my control volume now. If I am ignoring the inlets and outlets for the coolant, so this rectangular block is now my control volume. So what I will concern myself is with the air that is going in, the velocity of the air, that I would like to write it as W. So this velocity of air will be the same as the velocity of the car. That is my second estimation regarding the quantities. First I estimated about the volumetric flow rates, and now I am estimating the velocity of the air going into this radiator. So next is the velocity of the control volume. So it is fixed inside the car, so it will be equal to the velocity of the car. So this is the stuff on the left hand side. Let's write equations for the right hand side of what happens when the flow passes this radiator. So there will be V2, the absolute velocity of this air going out of this radiator, and the velocity of air that we will see when our reference point is this control volume. So here for W2, my reference point will be this control volume, that what is the velocity of air that is going out of this radiator, but the reference point of this velocity is this radiator itself, because this radiator is our control volume. So the reference point for this velocity is our control volume, that is our radiator. With this velocity is my absolute velocity, because its reference point is somewhere stationary on the ground, it is not moving with the car. So this is from where I can say that this was an observer somewhere stationary on the ground, and the car was moving by, and he observed the velocity, and when he observes this velocity, this will be called the absolute velocity, whose reference point will be the stationary observer, whose position again will be fixed with some arbitrary coordinate system, x, y, z you would call it, okay, whose position is itself is fixed regarding some arbitrary Cartesian coordinate system, and he is seeing this velocity as such, and for this velocity the reference point is this observer, and for this velocity W2 the reference point is this control volume. That's what we did in the airplane case for the jet engine. So if I would like to write velocity V2 in equation for this, so I would like to write it as V2, that is the absolute velocity, will be equal to the velocity of the control volume plus velocity of the air coming out of the radiator, but measured with reference to the control volume. So this is what my final equation will look like, and now based on the values given and unknowns, I can use this equation to calculate any of my parameters. So this was the estimations that I did. You can disagree with this, you can make your own estimations and come up with your own assumptions and estimates and equations. So you are free to do it, and please do it and change these estimations and play with this equation. Let's see what happens when we do not take this assumption. So what will be the knowns and unknowns in that case? So you are free to do that. Please do it. Okay, moving forward. And yes, this is the Reynolds transport theorem that we are going to be using for this scenario. And again, this is my mass conservation problem, so this is equal to 0. I will like to assume that my flow is steady. This will also be equal to 0, and then I'm going to apply it on my control volume on the controlled surfaces. Here the controlled surfaces are, you can take this as section 1 and you can take this as section number 2. So these two surfaces can serve as your control volume, but as you can see, it is already very much clear from what we did here. So you apply this equation on these two control surfaces, and you get equations like in terms of flow rates, and those flow rates with its area can be calculated if we are given some values. So use this equation also. Now we have a problem of a deforming control volume. So in this case the volume is stationary, but it is deforming. So our Reynolds transport theorem will look different in this case when we solve for this problem. So it is basically a syringe is used to apply a vaccine. If the plunger is moved forward, this is the plunger. If it is moved forward, at a steady rate of 20 millimeter per second. So this is the velocity of the plunger, that is 20 millimeter per second. Mind the units, they might be changed later or not. Let's see. And if vaccine leaks past the plunger at 0.1 of volume flow rate out of the needle opening. So this is the needle opening, and they say that the leakage is 0.1 times of the flow rate going out. So if this is the Q for leakage, then it is equal to 0.1 of the flow rate that is going out of the syringe. This is what they are saying. Calculate the average velocity of the needle exit velocity. We are required to find the velocity at this exit. So we would call this V2 or V out, whatever you want to call it. The inside diameter of the syringe and the needle are 20 millimeter and 0.7 millimeter. And so the inside diameter of syringe is given. This is the inside diameter of the syringe, which is equal to 20 mm, and 0.7 mm is the inside diameter of this needle, and it is 0.7 millimeters. So I guess we don't have to go from millimeter to meter because everything is given in millimeters. So we will just also like to find our final velocity in millimeters, and then we can convert it into meters, or maybe we can do that. So let's see. So this is what the data is given, and now we are going to write an equation for it, and this is what my equation will look like if I remove this. This is my Reynolds transport theorem, and because it is a mass conservation problem, so the left hand side will remain 0, and now this term will not be equated to 0 because it is changing, it is deforming. My control volume is deforming now, so I cannot take this term here equal to 0. So what will I do with it? I will integrate it with for this changing volume and see what I get. So I will get partial or partial t and rho and v plus there are two control surfaces, one is here and one is here, that exit of this nozzle, so you can take it somewhere here. So these two control surfaces that I've just taken, and now I'm going to write this term for these two control surfaces. So one will be my, if I integrate this again, I will get, let's go through it again. If I integrate it for this differential area, I will get rho v a. So this is my mass flow rate, and in this case the liquid is the same, so the densities are not going to change, so I can take out this term, or maybe not right now because I will need to solve this first. So this is what I'm going to get when I integrate this rho VA, and now I'm going to write this rho VA for section 1 and section 2 because these are my two control surfaces. So that will look like that is my fluid going out. There is no fluid going in this case, so both are this is fluid going out and this is my leakage, so both are going out, so both will be positive. So that is rho A1 V1 plus rho A2 V2 equal to 0 because I have equated this to 0. Now I'm going to simplify this a little bit further. So T into rho, and if I take it as area, that is area into length, that is the area of the plunger area, and the length of this syringe. So I have represented the volume as area and length. So now I will apply my partial term in next equation, but first I need to do some simplification here. This is at my section 1, and at section 1 my liquid is leaking, so I can also write this as, that is the flow rate around the liquid that is leaking, and I can from my data given see that my Q for leakage is equal to 0.1 of Q2, means this term. Okay, so I can write this in terms of 0.1 into rho A2 V2 plus rho A2 V2. So now we can see our equations are somehow simplifying themselves, and now I'm going to write it this term in terms of this. I'm going to apply this partial term, partial over partial t, this partial change with respect to time to this length now. Why this length? Because this length is going to change. When this plunger moves forward, this length will change with time. So I'm going to apply this partial change with respect to time on this length now. So my equation will look like rho A partial L over partial T. Okay, and this is my density rho plus, and one I'm going to add these two terms. One is 0.11 has a 1 that you cannot see. Now you can see it. So when I add these two terms, I get 1.1 rho A2 V2. So this is our equation. Now this is our equation equal to 0. I'm going to simplify it here now further, and if I can write it a little clean, it will be rho A1 partial L over partial T plus 1.1 rho A2 V2 is equal to 0. So this is what partial change in length over time. I can write this in terms of this. This is actually the velocity of my plunger, that is equal to partial L over partial T, because this is change in length over change in time. So this is what velocity is equal to, and this will be my plunger's velocity, that is moving at 20 millimeter per second. So that is when this length will change with respect to time is giving us actually our velocity of plunger. So this is what we are going to replace this term with, that is rho A1 velocity of the plunger will be now put here plus 1.1 rho A2 V2 is equal to 0. So now you have this equation, and what you needed to do was to find V2. You can find A1, that will be done by taking the area for this plunger, and A2 is the area of this syringe, so that can be, this term can be used, 0.7 mm will be used to find this area. You know velocity of the plunger, that is given as 20 millimeter per second. Densities can be moved out and equated to, divided by, can be equated on the other side, 0 divided by density, so these can be neglected, and you get a simple equation in terms of V2 is equal to A1 over A2 VP velocity of the plunger over 1.1. So this is what your final equation will look like. Put some values into it and solve it. You will get your answer in millimeter per second, and then change it into meter per second. Please do that for your own good and practice. So this was the case of a deforming control volume, where the control volume was deforming. It was not same as we considered throughout the previous problems. So this is your portion of finite control volume analysis, in which our mass was conserved throughout these problems, and the mass inside the mass of the system was not changing in any of these scenario. So the left hand side of the Reynolds transport theorem was equated to 0. And then we took some scenarios in which our control volume was fixed and not deforming, and we solved a problem and an example for that, and then we did a problem and an example of the scenario in which our control volume was moving but it was not deforming. We did a jet example in which we took a jet engine and then we estimated something for the radiator of the car, and then at the end we did a deforming control volume problem in which the control volume was deforming. A same example of deforming control volume is done in your Munson book, and it is the same case in which the syringe was injecting some fluid. So have a look at that one too. I would highly recommend it, because in that case our plunger velocity is an unknown and we are solving our equations for that. So please do that example also. And this is the end of the lecture. Thank you. So now we are in the second part of our finite control volume analysis, and in this part we are going to apply Newton's second law on our finite control volume and see what happens, because if you remember, we have to take a finite control volume now in which fluid will be passing, and we will now see its momentum, that what's this fluid momentum is going to do to the control volume under consideration. So this is what the Newton's second law tells us, that the time rate of change of linear momentum of a system is equal to the sum of external forces acting on the system. We remember the Newton's second law with a very famous equation, that is F is equal to mass and acceleration. So this is the force, sum of external forces acting on the system, and the time rate of change of the linear momentum of a system. So do you see a momentum term here? If we can write it as mv by t, we can write acceleration like this, velocity over time. So this terms become our momentum with respect to time. So this is the time rate of, if we take the rate of change of momentum of this term, so we get the time rate of change of momentum of the system is equal to the sum of all our forces. So now our extensive property in this case will be momentum, the rate of change of momentum. So if you remember extensive property with capital B, that was you saw this term in our Reynolds transport theorem. So now here B is equal to mv. B will be equal to, our extensive property is now our momentum of our system, and by system I mean fluid. In the previous conservation of mass section, in our extensive property was mass only, and now we have studied that portion. Now we are going to study this portion in which our extensive property of our system will be momentum. So moving on, we can write this in terms of values from Reynolds transport theorem, that if you remember this term as dV over dt, this is the rate of change of the system, but now instead of B we have put here m and v, and we have put m in terms of, but this is here our extensive property, and here mass is equal to density and volume. So this is our density and volume. So this is the mass term of our momentum, and this is the velocity term of our momentum. So now what we are doing is we are looking at the rate of change of momentum of the system. This is what this term, this statement is telling us, and this will be equal to the sum of forces that are acting on the system. So this term, my rate of change of momentum, will be equal to the sum of the external forces, and this is what I am going to replace. The left hand side of my Reynolds transport theorem is, I will replace it with this term, and whenever I will see a system, I will look to the forces that are acting on that system, and I will sum it all to the left hand side of my Reynolds transport theorem. So just to be clear about these terms, now moving forward, we get this term, that is our complete Reynolds transport theorem. So let's see, this is our this term, and this will be replaced by summation of forces in the system, and now this is our partial change of our system inside the controlled volume with respect to partial change in time. So we will be considering steady cases. So in steady cases, our time rate of change, partial change, will be equated to 0, because we'll be all looking at the steady cases only. And then comes our control surfaces, and in our control surfaces we'll be looking at terms like mass flow rates. So this term will mainly look like velocity into mass flow rate. Why velocity? Because here you see this small b. This small b is our intensive property, and it is equal to extensive property per unit mass. This is what the intensive property definition is, that it is extensive property per unit mass, and here our extensive property is what? Momentum, and this is mass. So these two terms will cut out to be this, and our intensive property here will be velocity, and the rest of the terms, that is rho, v and dA, that is rho, v and dA, will this integral will be applied on this differential area we will get in area A. So that this rho VA gives us m dot. So we will get m dot from this rho VA, and instead of our extensive property we will put here velocity. So this term, our control surface integral, will mainly come out as m dot v. So you have to remember this, because this is what we are going to do in our examples and problems. When any type of situation comes around, we will be looking at our problems like this. So this is what these terms are known for. Now moving on, this is what I just wrote, and I don't think so that this needs any further explanation, and I'll move on. So this is what our Reynolds transport theorem, when our extensive property is our momentum, states that the time rate of change of linear momentum of a system, this term, is equal to time rate of change of linear momentum of contents of the control volume. That is our fluid inside the control volume. But since we are saying that we are going only for steady cases, so that time rate of change will be equal to 0 plus net rate of flow of linear momentum through the control surface. That is the our fluid going in and out of the system. What is the momentum of that fluid going into and out of the system? So that momentum will be in terms of mass flow rate and velocity. So this is what our net flow rate will be. And so this is now our new Reynolds transport theorem for our linear momentum case, and this is what my final version of this Reynolds transport theorem will look like. That the left, now it is here the right hand side, but this is the change in system with respect to time. This is these two terms are the same, and here these two terms are the same. So now this is our final Reynolds transport theorem for this scenario, and we will be looking at fixed control volumes. In this case, we will be looking at fixed control volumes, and they will not be deforming. So non-deforming and fixed. So now moving ahead to our example to apply this new Reynolds transport theorem. Example 5.11 from your Munson book. The given as shown in figure. Let's see the figure. Water flows through a nozzle attached to the end of a laboratory sink faucet with a flow rate of 0.6 liters per second. So this is our volumetric flow rate. Q is, or what I would say is, Q at the inlet is 0.6 liters per second. The nozzle inlet and exit diameter are 16 and 5 mm respectively. This is the inlet, and as you see, the diameter at the inlet is 16 mm. So this will be our inlet, flow through our inlet, and this is our outlet. because they will be later considered when we talk about our control surfaces. These are our two control surfaces. Now the nozzle axis is vertical. The axis of this nozzle is vertical, as can be seen by this central line. It shows that the axis of this nozzle is vertical along the z-axis. This is the z-axis. The axis is vertical along the z-axis. The mass of the nozzle is 0.1 kg. We have been given the mass of the nozzle, so we have to consider the mass of this nozzle in this problem, and ultimately we will have to consider its weight and also the weight of the water. So the pressure at the section 1 is 464 kilopascals. At section 1 we have pressure. So one thing that is important is the forces. We are going to take some forces for this problem, and that force will be the first is the determine the anchoring force. The anchoring force required to hold the nozzle in place. This is the faucet, and with the help of these threads, this faucet is there is a nozzle that is attached to this faucet. This is the nozzle, and through it water flows. So first, it is our finite control volume problem. So this whole nozzle and water assembly is my control volume. I am taking both my water and my nozzle as my control volume, as shown by the blue dashed lines. So these are my control volume. And second, I will take velocity. So this is the velocity at the exit. You see that we have represented this velocity with W because this shows us the Z component of the velocity. Similarly, W1 is the velocity at the inlet. Then again we will take some forces. So the weight of this nozzle will be taken along the negative z-axis. The weight of the water will be taken along the negative z-axis. The anchoring force will be upward. This is our anchoring force because this is the force that is required to hold this nozzle to the faucet. So it will be said to be in the positive z-axis, direction. And again we will have an atmospheric pressure at the outlet. So here the pressure is atmospheric. We'll come back to it. So this is our statement, and this is the parameters that are given. So now let's look at the solution and our Reynolds transport theorem. So this is how it looks like. This is the change of extensive property inside the control volume with respect to partial change in time, which will be equated to 0 because the flow is steady. And then there is the control surfaces. There are two control surfaces, one is at section 1, the other is at section 2. So we will take this term, the z-axis of the velocity, because velocity is along the z-axis, the negative z-axis, and rho v dA term as our mass flow rate. So this is what we are going to apply at our section 1 and section 2. And at the right hand side we are going to add all the forces, because we can remember that we have to add our forces, because this is what these terms gave us in the previous slide. So we have to add all the forces. So first one is the anchoring force. It is directed upward along the positive z-axis, so no negative sign, there is a positive sign here. Then weight of the nozzle, it is directed downward, so it is negative. Then the pressure force at section 1, our control surfaces will be subjected to pressure forces. So there are two control surfaces, one is at section 1 and the other is at section 2. So section 1 will be subjected to pressure forces, and also section 2 will also be subjected to pressure forces. So let's see what those pressure forces will look like. These pressure forces will be normal to this section 2 and also to this section 1. So these are my pressure forces at section 1. So they are also along the negative z-axis at section 1. So my pressure force, as you know, pressure is equal to force per unit area. And when I talk about the pressure force, it will give me pressure into area. So this is what this term is telling us. This is the pressure force at section 1, and that negative sign shows the direction. Then the weight of the water, because I've taken the weight of the nozzle, now I have to take the weight of the water. Weight will be of water will also be directed downwards, so the negative sign here. Then my pressure at section 2. At section 2, the nozzle is exposed to the atmosphere, so an atmosphere will apply pressure force from outside, so that is why its direction will be upward along the positive z-axis. So that's why the plus sign and the pressure and area at section 2. So these are the things that are given to me to solve this example, and this is again in this case our extensive property is our momentum. And let's go forward and see what the solutions tell us. This was our governing equation, and this is my free body diagram for this particular example. These are all the forces that are shown. This is the positive z-axis, and I'm taking all the forces in the direction, in the axis of the flow. This is very important because in coming examples and problems, this is what we are going to do. We are going to treat them as one-dimensional flow problem. That the flow is occurring in one dimension. Here the flow is occurring in the z direction, in the negative z direction, and this is how we will define our forces also. We will take all the forces in one dimension only. This is very important because this is how we simplify our problem. So as you can see, all the forces are in one dimension. Their direction can change. They can be along the positive z, along the negative z, but overall their dimension will not change. They will remain one dimensional. So this is our anchoring force. This is the weight of the nozzle. This is the pressure force that is being applied at section 1. This is the velocity at section 1. This is the weight of the water. This is the pressure force applied from outside by the atmosphere at the section 2. This is section 1, this is section 2, and this is the weight of the water at the exit W2. So everything here is represented along the positive or negative z-axis. This is what we discussed in the previous slide, so I will not go through it again. Now our left hand side, as you can see, is written in terms of m dot v. This is what I explained. I will go through it again. This is my left hand side of this equation. So this is what comes out for section 1 and section 2. Flow rate at section 1, flow rate at section 2. So we have two terms. One is the flow rate, mass flow rate, and one is the velocity. Then again there is the mass flow rate and velocity. So this what comes out of this term when I apply this integral to my control surface. So this is my velocity, and this rho v and dA comes out to be area when this integral is applied. So I get W into rho v a. So this is my m dot, and this is W. So this whole terms come out to be W and m dot. Now I have applied this to section 1 and section 2, so I have gotten these two terms. Now let's discuss the plus minus sign. So the flow rate into the system. So into the system flow rate is negative, as you know from our previous discussions, that flow into the nozzle will be negative. Flow into the system is taken as negative. Then minus W1 because velocity is also a vector quantity, and that velocity is along this negative z-axis, plus M2 mass flow rate at section 2 for fluid going out of the system. So this is for the mass flow rate fluid taking place outside this nozzle, and a positive sign for it, because we know that the mass flow rate out of the system is positive. And then again the negative W2, that shows the negative direction of this velocity W2, and then is equal to the right hand side of our equation. These are all the forces: the anchoring force, the weight of the nozzle, the pressure force at section 1, the weight of our water, and the pressure force at section 2. Now we want to find the anchoring force, so we got this equation and we got this by just shifting some terms to the right and leaving one anchoring force term to the left. So what we will assume is that this is a mass conservation problem also, that overall our mass is conserved. It means that the mass that goes in and the mass that goes out is equal to the same thing. So our mass flow rate is the same. It means our mass is conserved. That is what we did in the previous mass conservation section. When overall we considered that mass is conserved, so here we are also considering that the mass is conserved. And if we apply this equation to equation number 4, then m1 and m2 will come out to be a common m, and we will get this term, m dot w1 minus w2, because m1 is equal to m2, m dot 1 is equal to m dot 2, so they will come out to be a common from this equation, and then the other terms will remain as such. So this is my final governing equation, and now I will put some values in this to find my anchoring force. Some are given and some will be derived, like the velocity at section 1 is not given, so I will have to find it from my volumetric flow rate, because I know my volumetric flow rate at section 1, it was given in the statement, so I can also find the velocity. So ultimately I can also find my mass flow rate from it, because volumetric flow rate is area into velocity, and my mass flow rate is rho v a, same density, velocity and area, and here my volumetric flow rate is area into velocity. So I can find my velocity W1 and W2 from this m dot, and this m dot in terms of volumetric flow rate was given to me at section 1. I guess it was 0.6 liters per second. 0.6 liter per second. So I will take that as Q1, and from that I'm going to find my velocity at W1, W2 and my mass flow rates. So this is how we are going to do it. So let's move forward. So let's first find our mass flow rate. We know that our mass flow rate is equal to rho W1 and A1, and this whole terms comes out to be into density and volumetric flow rate. We know our volumetric flow rate, so we can find our m dot by just putting in values. This is the density of water, this is the volumetric flow rate that was given to us in the statement, and this is the term multiplied to this term to convert it into meter cube per second from liters per second. So this is what our 0.599 kilogram per second is our mass flow rate. Now we are going to use the same volumetric flow rate and use this equation Q is equal to A1 W1 to find our velocity at section 1. Here we will use the area for section 1. So this is what this term is doing. Then we are going to find the same area and velocity using this volumetric flow rate to find the velocity at W2 by taking the area at section 2. So this is what will come out. Then I am going to take my weight of the nozzle, take the mass of the nozzle multiplied by gravitational acceleration. This will comes out to be the weight of the nozzle. Now I am going to find my weight of the water. So weight of the water is W is equal to mg, but mass of the water is not given, but we can use the rho v term for mass to find our weight of the water. So This is here mass is being represented as density into volume. So we know the density of water, we can multiply it by 9.8, but we need to find the volume of water in this nozzle. So this is the volume formula that is being used to find the volume of this nozzle. So what is this formula? This is a standard formula for a truncated cone. As you can see that our nozzle is like a truncated cone. So this is a standard volume formula for a truncated cone. If I may show you, this is a truncated cone and these are the different terms that are being represented here. So if you can see that this is let's say my nozzle. This is my nozzle. This is my section 1. This is my section 2. So here 1 by 3 pi r1 square. So radius r1 square plus r1 into r2. This is my r2. So this is r1 into r2, the radius as section 1 and section 2, and my r2 square. So r2 is the radius at section 2 and its square into height of the nozzle. The height of the nozzle was given in our diagram. So we will take that height and multiply it in this formula to these other terms. So this is what this formula was used also here. So here 1 by 12 represents the whole volume pi h. D1 square is our diameter at section 1, D2 square is our diameter at section 2, D1 into D2. So these are the terms that are given as radiuses, but here we are taking diameter, and you know that r is equal to d by 2. So if I take r square, so I will have to square this term too, so it will come out to be d square by 4. So if I take 4 here, write 4 here, d2 square by 4, and when I multiply d1 and d2, so I am basically multiplying d by 2 into d by 2. So that also gives me a numerator of 4. So if I take 4 common, so I will be having a term 1 by 4 multiplied by this 1 by 3 here. So this is why you get the term 1 by 12 into pi h and d1 square plus d2 square plus d1 into d2. So this is just a standard formula of volume for a truncated cone, nothing else. So this is the volume that I am going to use to find my weight of the water. Here you have to be mindful that the diameters are converted into meters. The diameters were given in millimeters, and the areas as such also will be calculated out to be millimeter square. So you have to convert them into meter and meter squares to get the volume of meter cube. So you have to be mindful of the units. So the weight of the water will come out to be 0.0278 Newton. Now we have all the known values, and we will just put it into our final equation to find our anchoring force, and all these terms will be solved. This at the end is representing our P2A because P2A2 because at section 2 of the nozzle the pressure was atmospheric, and you know when the pressure is atmospheric we equate it to 0. So this is what the 0 is representing. All the other values that were known and that were calculated are put to find the anchoring force, and at the end the anchoring force turns out to be 77.8 newtons. So this was our example. Now let's see a problem like this. This is a problem from your exercise 5.39, and this is the exact same scenario that we solved here. So you have to solve this yourself. The main difference are the units. The previous example was solved in SI unit system, and here the system of units is English. So this whole problem will be solved as such in English system of units to contain the dimension homogeneity, but all other scenarios are the same. You have to find the same anchoring force here. So just do what you did for that example and solve this problem. There is nothing different here. And use this equation also, because this is our governing equation for our momentum conservation. This is a problem again from your exercise problem 5.45, and here flow is passing through a pipe and nozzle assembly. This is the pipe and this is the nozzle. So we are going to find a force, an anchoring force for this assembly. So let's read the statement. Determine the magnitude and direction of the anchoring force. Anchoring force needed to hold the horizontal elbow and nozzle combination shown in figure in place. Atmospheric pressure is 100 kilopascal. Absolute pressure, the gauge pressure at section 1 is 100 kilopascal. At section 2, the water exits to the atmosphere. So at section 2 we have atmosphere. There are two sections that I am going to take. They are already mentioned here. One is here section 1. This is my section 1, and the exit of my nozzle is section 2. So let's go through the equation first. This is my equation for this problem that I have used quite often now. This is what will turn out to be 0 because I am not considering the change inside the control volume. This is a steady state flow problem. What I am going to do is I am going to take the mass flow rate at section 1 and section 2. So this term will come out to be U m dot 1, that is minus m dot 1. Let's write it like this. Then that is U inside the bracket and minus m dot 1, because at section 1 the fluid is entering the control volume. So it is the mass flow rate of the fluid going in, plus that is my velocity minus u2. This is my velocity. This is along the z-axis, so that's why I am using the u vector sign. This is u1. This is velocity at point 1, because as you see this is our x and y axis. So my velocities are along the x-axis. One is along the positive x-axis u1, so I have taken the positive sign. The other is along the negative z-axis, so I have taken the negative sign, and ultimately it will be multiplied with m dot 2. So this is the mass flow rate of the liquid going out. So these will be my terms on the left hand side of this equation. Now for the right hand side, this is my left hand side of this governing equation, and now for the right hand side, let me write all the forces. So the forces that will be occurring on this assembly are the pressure forces at section 1 and section 2 and the anchoring force. So the anchoring force, what I am going to assume, as I told you earlier, that we will take all the forces in the direction of the flow. So the direction of the flow that I have taken is along the x-axis, because my velocity at entry and exit is along the x-axis. So I am going to take the forces also along the x-axis. So my anchoring force will also be along the x-axis, but I have to assume one thing, that I have to assume is the direction, that either it is along the positive x or either it is along the negative x. So what I am going to assume is that it is along the positive x, and I am going to call it, let's say, Rx. That is the anchoring force that is required to hold this assembly, and I have assumed to be in the positive x direction. So I would write the right hand side as Rx. And then for my fluid that is going into the system, the forces at section 1 that it will exert is pressure force P1, A1. it is in positive direction, so this will be P1 A1. It is along the positive x-axis. This force at section 1, this is the section 1, and this is the force at section 1 is F1 is equal to P1 plus A1. Now my section 2 is exposed to atmosphere, so this is my section 2, and this will be the pressure force on this section 2 from the outside by the atmosphere. So there F2 will be equal to P2 A2. This is again along the positive x-axis, so this will be plus P1 A2. So this is how the right hand side of my equation will look like. Now I will see what is given and what is not given. What is given to me is the velocity at section 1 and the pressure at section 1. The pressure at section 2 is taken to be atmospheric pressure, and that is 100 kilopascal. So P2 is also 100 kilopascal. I am given the diameters, so I can find A2 and A1. Diameter at section 1 is 300 millimeter, at section 2 it is 160 millimeter, so I can find A1 and A2. So again I will make that assumption that overall my mass is conserved. I will also take that as a conservation of mass problem. So what I will write first is M1 dot is equal to M2 dot is equal to M dot. So now my left hand side of the equation will look like this. That is, let's write this equation. That is minus M dot V1 minus M dot V2 is equal to my right hand side of the equation, that is P1 A1 plus P2 A2 plus Rx. This is what I'm going to find. Now I can take minus M dot and V1 plus V2 is equal to P1 A1 plus P2 A2 plus Rx. So here I can use this assumption to find my velocity at point 2, because my velocity at point section 1 is given, but at section 2 I don't know my velocity. Sorry, these are U, these are not V's, these are U's. Velocity in the z-axis, so U1 and U2. So U1 is given, that is 2 meter per second. I am going to use this term here, like rho A1 V1 is equal to rho A2 V2. So density is the same. I will be left with A1 V1 is equal to A2 V2. So I will use this equation to find my velocity at section 2. So, or I would say U2 is equal to A1 U1 divided by A2. This is a circular assembly, so my area will be pi by 4 d square, and diameters are given in millimeters, so please convert them into meters and again solve for this. Be mindful of this, these units. I am saying this again and again because they can make a huge difference in your final answer. So the rest of the terms are known to me. I know the pressure at point 1. I know I can find out the area at point 1. I know the pressure at point 2. That was the atmospheric pressure given in the statement. I know the area. I need to find this Rx. So I will solve this equation for my Rx, and what I will get is a negative answer, and the answer will be 8340 Newton, but the sign will be negative. It means that my initial assumption that Rx is along the positive x-axis is wrong, and the anchoring force that is required for this assembly is Rx, but its direction is not along the positive x-axis, but its direction is along the negative z-axis like this. So this is the anchoring force direction, and the magnitude is 8340. So this was our problem from your exercise problem 5.45. The same example like this is solved in your textbook. After the nozzle example, there is an example just like this, but the main difference is that at section 2 there the pipe cross section is the same. Here a nozzle is attached, but at section 2 there is no nozzle. So but overall the problem is the same, so it is very interesting. Please go through it so that you might clarify your concepts, and please try these problems yourself too.